Excellent. It's a great pleasure to welcome Swapnamay Mondal, who is joining us from Trinity College. And he's going to join us again, officially here as in person even, in October, I believe it is.
Yeah.
So he's going to tell us about scaling black holes and modularity. And again, I want to thank you for joining in us and giving this talk at very short notice. So thanks again for bailing us out on that.
Thank you. Thank you, Genjo, for the invitation and the opportunity. Yeah, so I'll be talking on scaling black holes and modularity. It's based on a work that I recently did with Aradhita Chattopadhyay and Yan Manshot. Yan, you know, and Aradhita is a postdoc at Trinity. I think my slides might be a bit, there might be mistakes here and there and so on. So do interrupt me. And yeah, I might have forgotten to write stuff. So yeah, do ask me questions. Okay, so let's summarize. In this talk, I'll talk about black holes in n equal to 2 string theory. And there, along with usual single-centered black holes, you happen to have multi-centered black holes as well. And our object of study, as the title suggests, would be a special kind of multi-centered black holes, which are called scaling black holes. They're called so because their distances are not quite fixed by relevant equations. They keep like a scaling degrees of freedom. And in particular, that means that the various centers in such a black hole bound state, the centers can come arbitrarily close. And in more than one sense, this nearly coincident regime of these black holes, they resemble single-centered black holes, that is the usual black holes, which means that whatever study you do about single-centered black holes, they are, you must include such black holes in that study. Otherwise, the story is not really complete. Now, with black holes, the main thing we do in string theory is to study their degeneracies. This has to do with the reproducing the black hole entropy. And
can I just ask a question?
Yeah, sure.
Sorry, it's very early for a question, but this is fundamental to me. What do you use as the definition of a center? What do you define the center of a black hole to be so that you can have multi-centered ones?
Oh, no. Okay, by center, I just mean one black hole. Like, I mean, if there are 3 black holes forming a bound state, I just call that 3-centered black hole.
Center must mean the singularity or the metric. Real
no, I do not mean geometric center. It's maybe a bad word.
Sorry?
So what do you mean then? If you mean 3 black holes, why do you call them scaling black holes?
There will be 3. Let me ask one question. I remember...
I haven't finished answering mine yet, though.
Long ago, I heard a seminar by Chandrasekhar where he talked about no n equal to 2, just several black holes which are stationary related to each other. I think they are something like Lagrange points in 3-body problem. Okay, and he talked about it and tried to discuss this thing. So why does one need supersymmetry at all? I thought center means where there is an actual singularity to the metric. Let's r equal to 0 in the Schwarzschild coordinates. Am I not right?
Yeah, but I do not mean a center in that sense. Maybe I should have used a different word. So don't think too much about the word center. I mean, I just mean 3 constituents, constituent black holes. That's what I mean.
So then we come back to this question that was asked by what is the meaning of statement that there are 3 black holes? How does one define?
There are 3 event horizons, for example. Individual black holes will have their event horizons.
But how do you separate them? There will be a gravitational field all over the place.
Yeah.
So I think the issue is how does one say there are 3, 10?
Well,
in the same sense, we say that
pi zero. I would say pi 0 of the horizon, the null surface, is 3. To use a more mathematical statement of what you mean.
If they're separate, but they could merge.
Yes.
Only in very certain cases,
Yeah.
not always.
Horizon is not a real singularity. But anyway, I want to
No,
ask,
but horizon is a physical entity, Well, it's a null surface.
but you cannot detect it. You have to go to infinity to say that there is something.
No, you can define it mathematically as a null surface.
Yes.
Yeah.
It's a property of the metric, and the metrics he's talking about are static. So
Yeah.
merging entities are not static. So either they I don't believe he will find anyone where he would have pi0 being 3 or being 1 and you could consider it 3 black holes. If they're merging, then it's a highly dynamic situation.
Yeah, but I mean, that's likely sidestepping the point that they could get very close and touch.
He can probably tell us that they won't be able to touch.
Not if it's not dynamic.
Yeah, they're static. There is no dynamics here.
Yeah.
Let me again ask, why does one need supersymmetry for this? Because I remember that there are such solutions for the standard Einstein theory. At least that is what I remember.
Yeah, well, so as I understand, it has to do with them being static because, of course, they'll attract through gravitational attractions. So they need something to repel them also. And so you need like forces, extra forces. And those gauge fields and gravity, when you put all those things, they come in supersymmetric multiplets. It's the other way around, really. I mean, I don't have an argument that it had to be supersymmetric to be static, but the other way is true. They turn out to be static.
I do remember that Chandrasekhar has discussed it long ago, and there were black holes which was separated, but my remembrance is black hole means there is a singularity at the center, but that appears not to be the case here. And there was no supersymmetry. And he was discussing he was trying to solve the equations and study them.
No, I think singularity would still be there at the center.
Sorry?
I think singularities would still be there at the center.
There will be 3 singularities for him. Here there is no.
Yeah, I think so.
Okay.
Yeah, but for our purpose, we would not really need to go inside the black hole. Our story would confine to the horizon.
Okay.
Yeah. So in this context, are there any questions?
With the talk. I say, please proceed with the talk. I'm curious now.
Okay. Okay. Yeah. So what was I saying? Yeah. So our main concern in this sort of situations is the black hole degeneracy and checking the entropy and so on. And in string theory, it often happens, and with because of certain reasons that I've explained, these generating functions of degeneracies, they happen to have interesting modular properties. So what we do in this talk is we would look at the modular properties that the contribution. Okay, the scaling black holes give certain contributions to the degeneracies, and we'd ask what modular properties do they have. And for black holes with 3 centers, they will turn out to give a depth 2 mock modular form, and we'll compute its modular completion. That's a broad summary. Now I'll get in more detail. So first, let's quickly recap why black holes are important in the context of string theory. It's standard folklore now, as well known, that black holes, although classically they do not have any entropy, simply because there is no scope for microstructure, quantum mechanically they do. And we have a very precise formula for black hole entropy, which is 1/4 of the area of event horizon in Planck units. Now, this gives an immediate puzzle, because in our classical understanding of black holes, there is nothing that could give rise to the entropy, because there is no microstates. So how does one understand this entropy from a statistical mechanics point of view? That is the puzzle. but the formula itself gives a clue where we should look for answers. This LP is the length scale of quantum gravity, not of string theory, of any theory of quantum gravity. I mean, not particular to string theory, I mean. So answers should lie in a consistent theory of quantum gravity. Now we can turn the tables and use this as a test for any candidate theory of quantum gravity, whatever that might be. And string theory does succeed in answering the question. The broad structure of the logic is as follows. So is my cursor visible? Hello?
Yes. So you're sorry, move it again.
Can you see that?
Yes, yeah, yes, we can, yeah.
Okay, good. So this is where string theory is originally defined in 10 space-time dimensions. And before we talk about black holes, we need a theory, a 4-dimensional theory of gravity. So what we do is we dimensionally reduce this 10-dimensional theory over a 6-dimensional space, Calabi-Yau threefold, and then we get a supergravity theory in 4 dimensions. And in that theory, there are black hole solutions, and we are talking about those black holes. The good thing in string theory is that black holes really appear in 2 avatars, if you wish. This is one, the standard one. You have a supergravity theory and black hole solutions there. Now, the supergravity theory has a lot of gauge fields, and black holes carry charges under those gauge fields. Now, you can trace back those gauge fields in the full string theory as higher form fields. Most of them are Raymond higher form fields. And just like in the gravity, their charges are carried by black hole. You can ask the same question in the full string theory. And then you find that these charges are carried by membrane-like objects, the d-branes, or in M theory it would be M-branes. So in the full string theory also you have, like just by tracking the charges, you start from the black hole and you get to this d-branes. So they're complementary descriptions of the same object. Now, in the black hole side, you have the area formula of the entropy, but you have no idea about the microstructure. And in the d-brane side, there is no area and therefore no area formula either. But you can write precise Lagrangians, Hamiltonians describing their dynamics, and therefore you have a very clear understanding of microstates. So you can count them to produce the entropy. So people count these microstates and check if they match with they produce the entropy of the corresponding black hole. And in all cases that people have checked, they do. So at the very least, this provides a good validation in string theory. So one good reason why you should continue studying this problem. Okay. Now I'll get to the scaling black holes. Any question till now?
Yeah, I'm just curious. Does that argument work with 11-dimensional membranes?
Yeah, we would use them actually.
So I can count the. So what am I counting to get in to get the?
We would actually compute the index.
Okay. All right.
Yeah, I didn't tell it here, but
so it's the index is not counting charges. That's
no. The index is counting the number of bosonic ground states minus the number of fermionic ground states.
Yeah, no, that's fine. That part I understand. But you said that you were going to relate it to the number of charges and the counting of the possible ways of combining the charges.
Oh, did I say that?
Or maybe I misunderstood. Okay. Okay, then that's fine. If that's not what you meant, yeah, you just meant the index. You're going to count it as an index. Yeah, that's fine. Okay.
Yeah. Yeah. So now scaling black holes. First, let's talk about multicentered black holes. Here too, there are like 2 pictures. It's good to start with the microscopic picture. So we just learned that the black holes can be thought of as like stacks of d-branes. And when you have multiple black holes in the microscopic picture, that might lead to more than one stacks of d branes intersecting each other, and then there would be strings stretched between those different stacks of d branes. And such a system can be very crisply described by a Kuiper quantum mechanics. For that, what you do is you draw a diagram of this sort, where there are some nodes correspond to stack of d branes, and you associate in 4-dimensional language dimensionally reduced to one dimension, that is just the time. They will have n equals to 1 vector multiplets. That would be their degrees of freedom. And then there would be strings stretched between various d branes, and they would correspond to their degrees of freedom would be the chiral multiplets. In fact, the degrees of freedom of the stack of d branes are quite intuitive. The bosonic parts of them are simply how many ways the d brane can move, etc. Okay. You can further simplify this Kuiper quantum mechanics description by integrating out stuff. So in particular, you can integrate out the fields corresponding to the nodes, and that will give you an effective description in terms of the chiral multiplets that correspond to the arrows. This is called the Higgs branch, and we will not use it in this talk. The second equivalent description is to integrate the chiral multiplets out, and then you have a description in terms of the nodes, so to say, and this is called Coulomb branch. This is useful for us because we can think of these nodes as individual black holes. So this is what I meant by centers. It's a bad word, perhaps confusing word, but I just meant this. So for us, this would be multicentered black holes. And now we would like to know what are the equations that constrain their position and so on. These are called Deneps equations, and they're pretty simple. So Rij is the distance between ith and jth center. Gamma i's are charge vectors. There are electric and magnetic both charges, and this thing gamma I, gamma j within brackets. This is this DSG product, which is defined like this. In the right hand side, we have certain parameters called Ci. They are defined in terms of the central charge corresponding to those individual black holes. So the input really here is, there are two inputs. One is the charge, you see the gamma I here. And the second input is the T, which is the moduli fields. So string theory has all these fields whose values are not fixed by the equations of motion. You are free to choose them at infinity. So T's are those. Their values at infinity determine these parameters. Now, here Rij being distance, they are positive. So you can imagine that depending on the these exact parameters Ci, it might be that sometimes you do not have positive solution for Rij.
You probably said, and I missed it, what is Z?
Z is the central charge for the ith center. I have not written an expression yet for Z. I'll do that later. But we do not really need the Z here. We just really need this Ci, these numbers.
And is there any intuitive understanding as to why this looks so classical, like Coulomb or classical gravity, Newtonian gravity? This 1/r potential? Is there some Gauss law constraint or something like that that's forcing it?
Yeah, in the supersymmetric quantum mechanics, one has a potential of this sort. It indeed comes from minimizing a potential. But no, I don't have a good intuition for that.
Okay, that's fine. Yeah. It just is striking that it's so. It just looks like some classical Newtonian mechanics problem.
Yeah, it doesn't quite come that way. I mean,
What is little a?
sorry, little a?
Yeah, or is it an alpha?
Oh, sorry. So e to the I alpha is the phase of the central charge for the like total system.
Oh, so Z is just a pure number, and that's its phase.
Yeah.
Okay.
It's not the phase of this Z. So Z is a function. This is Z of gamma I for the ith center.
Mm-hmm.
But e to the I alpha is the phase for Z of like total gamma, the total charge of the bound state.
Mm. Why would it enter additively inside the exponential?
Sorry, what do you mean by why would it enter? Right.
I'm not quite sure why it should. I mean, that's an equation per gamma I, and you're saying that's the phase of the total central charge. I'm not quite sure why I should believe that's a plausible formula.
Well, when you have more than one BPS particles,
for us, but
sorry,
I presume there's a derivation of it, which you're
yeah
going to allude to maybe later.
No, I was not going to derive that, or yeah.
Okay,
but there exists a derivation.
Okay, and we're supposed to accept it. Okay.
Okay, we can accept it.
Yeah, I mean, in general, when you have more than one BPS particles, whether their central charges align or not, that typically becomes important.
Mm.
Because their mass and so on, these things depend. So it's not so unexpected that the phase might matter.
Mm.
It actually appears as Z bar of the total Z and then divided by mod of that Z, which is same as this.
Yeah, okay.
Sorry, just to recap, Z is the central charge of one of them. And it's the central charge of what algebra?
N equals to 2. Supersymmetry algebra.
Okay, so it's in the supersymmetry algebra. Okay.
Yeah. Yeah, so Z is a function. You just give gamma I in it, T in it, it will spit out a number. Yeah. So the crucial point for us here is that the solution of this equation might or might not exist depending on Ci. Very simple case is when you have just two centers. So there is just one equation. You have gamma 1, 2 divided by R1, 2 equals to C. Now, if that C is, suppose gamma 1, 2 is positive, then if C is positive, then you have a meaningful solution for R. But if this guy is positive, but this guy is negative, of course, R is going to be negative. That's nonsense. So that means that for those particular values of Ci, the solution doesn't exist. This phenomena, it's called wall crossing. That is, you change the moduli T, and suddenly you encounter a kind of wall beyond which a bound state that existed here, this side of the wall, ceases to exist in the other side of the wall. Or it might be the opposite way. So these are called wall crossings. Questions? Okay. So more concretely, we would be talking about this deeper brain black holes. That is, so in n equals to 2 theory, we are getting that theory by compactifying on 6 dimensions. So the kind of deep brains that you could possibly have wrapping the 6 dimensional internal space are D6 brains, D4 brains, D2 brains, and D0 brains. We are in type 2A theory, sorry. So that's why there are even number of even dimension of D brains. Now we make the choice that D6 brain charge is vanishing. It's important for technical reasons. So there is a D4 brain charge, which we call P. We'll also refer to it as magnetic charge. And then the Q is the D2 brain charge. And Q0 is the D0 brain charge. P and Q are vectors. They are multi-component objects, but Q0 is a number. The dimension of these P and Q, these vectors, it's the second Betti number of the Calabi-Yau threefold. This has to do with the number of ways the D4 and D2 brains can wrap the internal cycles. They all give rise to different kind of gauge fields, and therefore this electric and magnetic charges are multi-component objects. It's B2 because you have a D2 brane. You have B2 has many 2 cycles, and the D2 brane can wrap all those 2 cycles, and correspondingly you will have different kind of charges. That's why it's B2. Is it clear? Okay. Yeah.
It's not quite clear why the association would be with these Betti numbers. This is a 6-dimensional manifold, so you have B0, B1, B2, and B3 probably in principle that could be different.
Yeah, but for these Calabi-Yau triples, you have B1 equals to 0. And anyway, we do not have a D1 brane. We only have D2 branes. And
sorry, the dot. I thought ABC were referring to the Betti numbers B0, B1, and B2. But that's not what the dot means, is it?
I mean, it can take values from 1 to B2.
Oh, it can take values from 1 to B2. Okay, right. Okay. I
think it's bad preparation of slides. Sorry. I mean, there are B2 homologically independent 2 cycles. So D2 branes can wrap B2 different ways. And correspondingly, they'll show up as B2 kind of charges in the 4-dimensional spacetime.
No, it's okay. I'm just trying to catch up. This is a triple intersection number. Yeah. Okay. I'm catching up. Okay. All right.
Any other question? Okay. So one important input for us would be these triple intersection numbers. Because the lattices in which these magnetic and electric charges will live, the quadratic forms on those lattices, that is determined by these triple intersection numbers. So electric and magnetic charges will live on dual lattices. We call them lambda and lambda star. Another important bit is that this quadratic form, it has signature 1, B2 minus 1. So it's mostly negative. That would be important. Okay. So we talked about this modularity.
Before you go, just so I can try and understand a little bit. You say the magnetic charges live on some lattice there. So why is P the magnetic charge? P is the charge of the D4 brane.
Oh yeah, I mean it has to do with the way it appears in the 4-dimensional spacetime. It's not very important. If you call it something else,
so you're taking the D4 brane is a 5-dimensional object in 10. So yeah. Its dual will also be a D4, will be a 4-dimensional object. It just doesn't look magnetic to me. That's why I'm.
It's more of a conventional thing. If you call this D2 brane charges electric, then you can check the dual would be D4s.
I see you're just deciding that you want to call these electric.
Yeah, it's not very important.
I was trying to get why they were electric from.
I mean, it can't be absolute simply because we have these lots of dualities in string theory. You can always go to another frame and the meanings will change. Yeah. So the electric and magnetic doesn't have any absolute meaning in that sense. Okay. Yeah. Okay. So I stress that depending on this modularity, the existence or non-existence of these bound states depend. Now, one specific important point at this modular space is the attractor point. So for supersymmetric black holes, it so happens that whatever moduli you fix at the infinity, the structure of the the structure of the solutions are such that at the event horizon of the black hole, these moduli fields flow to a specific value that is decided entirely by the charge carried by the black hole. And it does not depend on what was the value of moduli at infinity, which I call T infinity. So this specific value that the moduli is attracted to is called attractor value. And it's we'll refer to it as T gamma, gamma being the charge. You change the gamma and this will also change. So the B field, it coincides with the QA, that is the electric charge, and the J field, that is which comes from which is the Kähler moduli, it coincides with the magnetic charge PA. Again, electric and magnetic are just names, not take them too seriously. And when you do that and you feed into the formula for this object CJ, I have not shown you the detail, but they turn out to have this expression. The important point here is that there's a minus sign that is important, and there's sum over gamma ij, j not equal to I. That structure is important. M is the mass of the black hole, which is not important for what we are going to do. Now, if you put this value of C in the Deneps equations, which was just this equals to Cj, and we are putting this. Now, first, just think of the simplest case where there is no sum and just two nodes. So you have gamma 1, 2 over mod, don't need the mod really, R1, 2 is positive. Then you have minus M gamma 1, 2. Clearly that this equation cannot have solutions, right? Because it essentially tells you that R is a negative number. The distance is a negative number. Hello, am I?
No, I'm just trying to understand how this came from the Deneps equation. Sorry,
okay, let me just.
There was an inner product of two gammas in the Deneps equation, and they cancel.
Sorry,
but there should have been a Z left on the right-hand side. And I was wondering if the star meant complex conjugation.
Oh, no. Sorry, something. You can't change it. Yeah, so the Deneps equations were this.
Yes.
We are just putting specific values at Ci, which I call Cj star. No, I don't mean, these are real numbers.
Okay, so that's the object you're putting in on the right-hand side of the Deneps equation. The gamma comma gamma I somehow cancelled.
Oh, sorry, I changed the notation here. Gamma ij stands for this inner product of gamma I and gamma j.
Okay, all right, okay.
I'm very sorry.
Sorry. And the mod of Z. Oh yeah, you're just substituting in this. Okay, yeah. No, then I understand it. Okay, it's the gamma. It's that inner product. Yeah. Okay. Yeah. Fine.
Because this gamma is sum of all the gamma j's, and this inner product being antisymmetric, the gamma I term is not there. So it's gamma ji sum over j, and since it's antisymmetric, I can take a minus sign out and write gamma ij.
Yes.
And I write gamma ij because it appears like that in the left hand side.
Yes, I understand. Yeah.
Yeah.
It was the change of notation that's wrong there.
Yeah, I should have explained better, more clearly. Anyway, so the point here is that, as you can see, that for two centers at this value of C, there are no solutions. It's not only a phenomenon restricted to two centers. In fact, if you have a like multi-centered black hole, you have a set of such equations. And if for any one of those nodes, it so happens that all gamma ij, that is, you fix I and change j, if for one such I, all the gamma ij's have the same sign, let's say all are positive, then the left-hand side for that equation is definitely positive, whereas the right-hand side is definitely negative. So it cannot have solution. So we see that at the attractor point, a great many multi-centered black holes cease to exist, which is very good, because if we just want to specify the total charge and want to ask stuff, then this simplifies the problem. Why can't I change? Okay, yeah. So then the question comes, who survives at the attractor point? So first note that the gamma ij's are, if all the gamma ij's are positive, that means you have outgoing arrows. It's a convention thing. We draw the diagrams like that. And if all the gamma ij's are negative, then all the arrows are incoming. So then the thumb rule is that your diagram must not have a source or a sink. And such diagrams, we call them such quiver diagrams, they invariably will have loops, because you start somewhere. Since there are invariably some outgoing arrows, you can go somewhere. Again, in that node, you'll have some outgoing arrow. You can go on doing this. And since there are finitely many nodes, at some point you'll come back, which means there would be loops. Here are some simple examples of such quivers. You can go on drawing them. Any questions at this point? Okay. Now, we have not talked about the Z in much detail, or we have really forgotten the detail of the black hole. We have been treating them as point particles and doing this stuff. But when you actually do a more detailed analysis, you will need like mass of the black hole and so on. And you would like to go to a regime where things simplify. And that regime happens to be a certain large volume regime. That is where these Kähler moduli, these JA fields are large. So you have one simplification at attractor point. You have a sort of complementary kind of simplification at this large volume regime. Of course, we would like to have best of both worlds. So we wondered, can there be an attractor point, some sort of attractor point, and in this large volume regime as well? And luckily the answer is yes. If you choose if you fix the moduli fields TA like this, that is, you still fix the B field to be Q, the electric charge, but for the J field, it's still proportional to the magnetic charge PA, but you put a number here, lambda, and you take that lambda to be very large. If you do that, you'll see that this C parameters that appear in the Deneps equation, they are proportional to their attractor values. Now, note that whatever we argued here, this guy M was absolutely unimportant. It's only the sign that mattered. So here also, at this point also, whatever analysis we did regarding the existence or non-existence of a certain solutions, those will continue to hold. Right? Is the point clear?
I think so, yes.
Okay. So we'll work in this large volume attractor point where we have a best of both worlds. Okay. Now, just to be a bit more concrete, here is, let's talk about the simplest quiver with loops, which is a 3-node quiver. You do not have a quiver with, you can't draw a loop with just 2 nodes, right? You need 3 nodes at least. Something very funny happens in the equations with Deneps equations, which are these. For this case, I have, for simplicity, named this gamma 1,2 as A, gamma 2,3 as B, and gamma 3,1 as C. So you have these very simple equations. Now note that if you replace, if you do replacements like this, for example, with 1 over R12, you have this extra term, which the A cancels with this A, and you get extra 1 over epsilon here when you substitute this. And from this term also, when you substitute R31, which is same as R13, also the C cancels and you have the same term again here. But then since there is a minus sign, they cancel out. Is this clear? So the equations are unchanged.
Yes.
Now, of course, the minus sign is very important here. And that the minus sign is there because one arrow is incoming, another arrow is outgoing. The outgoing one comes with plus and the incoming one comes with minus. So, I mean, it's intimately connected with the existence of loops. if you have to have that for all equations. Okay, so this means that you can choose this number epsilon at your will. So the solution space, you have a sort of tree direction in the solution space of these quivers. In particular, you can take epsilon to be very, very small. When you take epsilon to be very small, then it's like 1 over R12 goes like 1 over epsilon. That is R goes like epsilon. That is all the nodes are very close to each other. So R12 will go like epsilon times A, R23 will go like epsilon times B, R31 will go like epsilon times C. And in order for it to be a physical configuration, they must form a triangle, physical triangle, which means ABC must obey triangle inequalities, which is a condition on charges. These are called scaling solutions because there is a pre-scaling direction, and they're the topic of our talk. Note one amazing thing is that in all this argument, these numbers C1, C2, they did not really enter. So these solutions exist for all value of these C1, C2, which implies all value of the moduli fields, including at attractor point. So as we expect, these solutions exist at attractor point.
I missed where the metric for the triangle is coming from. Why is it? How do I know that it's a Euclidean geometry that I should, or how do I know that it satisfies a triangle inequality?
We don't. Oh, this is being done in a regime where you ignore the effects of gravity. You think of black holes as point particles, and we are working in that regime.
Okay, so you're working in the regime where you are on scales so far from the black holes that it's flat, and in that regime you're finding that they are, that A, B, and C have to form a triangle. Okay.
You are indeed right that one has to look at the geometry, and in particular, one has to make sure that there are no closed time-like curves and so on. Those are extra complications which we'll ignore. But and you're also right that for a random ABC, they will not satisfy triangle inequality, and they will not exist. So that's a condition. And this epsilon goes to 0 limit, as you can guess, is going to be tricky. Anyway.
Thank you.
Welcome. Just to give you a bit more insight about the structure of the the solution space of these scaling configurations. So these Deneps equations can be very simply solved by making these parameterizations. Again, epsilon is a pre-parameter here. You can put them in Deneps equations and find that they are satisfied. It's not a big deal. Okay, now so there are angular directions, of course. This is only a statement about distances. It's not talking about angles. But the distances themselves, this epsilon is not entirely free in the sense that there's a range to it. For example, if you take epsilon to be very large so that you can ignore 1 over epsilon, then you clearly see that the 1 over R12 becomes minus m, negative. So that's not allowed. So epsilon will have an upper limit.
But that's where I expect the flat geometry to be relevant, is when they're very far apart. So I'm not. I mean, R12 is some separation of the centers.
Yeah.
And I would like that to go to infinity so that I can ignore curvature and various other effects, so that I might be able to check that that their distances satisfy a triangle inequality. But now I'm not allowed to take them to infinity. So I'm not sure how you argue that.
I think the picture we should have in mind is like the following. Suppose you have a so suppose when you compute say scatterings of d branes and so on, scattering of a string of a d brane and so on, we take it to be in a flat space. We are in that sort of regime where we have non-perturbative objects, but we, if you wish, tune the Newton's constant so that we can ignore gravity.
Yeah, there must be another. Then the argument isn't self-contained the way I was understanding it. So okay. I will accept that it's. I just don't understand it, but that's okay. Go ahead.
Okay. So there is a upper limit to this epsilon, where, and it so happens if you work stuff out, you'll find that in this upper limit, the three nodes become collinear. Oh, I have. How much time do I have? I didn't check that.
Oh, we are very relaxed about time. There's no real upper limit until people get exhausted.
Okay.
We don't have teaching duties, so we're feeling freer.
Okay, but I'll be faster, I think. Okay, but the important point is that there is no lower limit to epsilon, and that makes this epsilon goes to 0 region non-compact. So very roughly speaking, the scaling solution space has a structure where you have a sort of finitely separated nodes or centers, which we'll call the regular part. This part is easy in the sense that when you want to compute certain, when you compute the index and so on in this solution space, the standard techniques work in it. The standard techniques capture only this regular part, and it fails to capture the very small R part, which we'll call the deep scaling part, where the centers are almost coincidence. This part is tricky, but this is not the topic of our talk really. Okay, why we are talking so much about this deep scaling part is because it's remarkably similar with single-centered black holes in more than one sense. For example, an asymptotic observer can't tell them apart. It can't decide whether it's just one black hole or three black holes which are arbitrarily close. Then both exist for any value of the moduli. This is also true for the regular part of the scaling black holes, by the way. Then another non-trivial point is that it has been appreciated lately that black hole microstates typically carry zero angular momentum. Now, for the scaling black holes also, there are certain zero angular momentum states called periodic states, and which can actually be retrieved from this deep scaling part. This is another analogy with microstates of single-centered black holes. Then when you turn on the metric and write down the explicit metric, then if you take this limit epsilon goes to 0, you actually find an ADS factor, which is standard for supersymmetric 4-dimensional black holes, like rotationally spherically symmetric. You get ADS2 factor. And the same similarity holds at the level of 5 dimensions. You can also work in 5 dimension. Then you can take a certain decoupling limit, which was done by this work, where people find that objects that are smaller than a certain length scale, they survive and go over to ADS, develop an ADS3 throat. This includes the black holes for which centers have D6 brane charges, but we are not talking about them. So then it leaves only single-centered black holes and scaling black holes because they can come arbitrarily close. This is a very non-trivial similarity. And as you would expect, this ADS3 is important because you expect it to be related to the microscopic CFT2 that describes these black holes, which means that in the microscopic description, there is no genuine difference between scaling and single-centered black holes. Any questions till now?
I think it's okay.
Okay, now we'll come to modularity, because the title was Scaling Black Holes and Modularity. And as you all know, the modular group is SL2Z. One important thing is that in our story, it appears in two fashions. One is, it is the self-duality group of type 2b supergravity, the S-duality group. And there you have this complex field tau, which is composed of this RR field and this dilaton. It transforms like this under S-duality. And other fields also transform, in particular the field coming from Kähler moduli, the J field. Okay, but we are not in type 2b, we are working in type 2a supergravity. But you can always T-dualize along the thermal circle, the time circle, and then things work again. There is, this is one way is this modular group appears. There is a second way, which is from the perspective of the microscopic CFT2, which I have not described. So these black holes can be thought of as like M5 brains wrapping a 4 cycle in the Calabi-Yau threefold and the M theory circle. And then one sort of reduces over the 4 cycle and gets the effective theory on the M theory circle times the time circle. Because
Sorry,
one is infinite. Sorry?
You have Euclideanized or something here?
Sorry?
Have you gone Euclidean? Is that what's going on?
Oh, yes, yes.
Okay, because, all right. So that's why there's a time circle.
Yeah.
Okay.
Euclidean. So then it becomes a theory on that torus. And as when you write a CFT on a torus, there is a modular group of the torus. So that's the second way. Now, it's not immediately obvious whether these two modularities are the same. It turns out they are, because you can check that the taus in both cases are the same. It's particularly simple to see this for the tau2. For example, if you start with the CFT side, the tau2, of course, is the circumference of the time circle and divided by the circumference of the M theory circle. And the time circle circumference is the inverse temperature, beta. And that of M theory circle is this. It's the point here is that M theory circle is, its size is fixed in terms of the fields, the GA, the dilaton. And then you see that if you just use this formula to replace GA in terms of GB, you precisely get this 1 over GB.
Yeah, sorry, your jump to Euclidean, I haven't kept up with it. My brain is just catching up now. The jump to Euclidean, what one would normally do is one would remove the singularity. There would be a conic singularity in the time, which would give me this time circle. But now somehow that has to work for this multicentered case. It's not at all obvious to me how that would work for the multicentered case. That I'm going to get just one circle rather than circles of different radii or do. The point is that if I have one black hole, then I know that its surface gravity is fixed along that one, but a different black hole has a different surface gravity. So I would expect the temperature to be related to the surface gravity. So, and that should be related to the periodicity. So where is one temperature coming from and one time circle with a given periodicity? Why is it a torus rather than a homogeneous surface? It's maybe another way of putting it.
Well, the first torus is not in the space-time really. It's in the M theory circle and the time circle.
Well, but yeah, my question is, why is the time circle? Why is the time circle a circle rather than a set of circles? Or what is going on? How do I Euclideanize that metric to get a single time circle with a given?
So when we are talking about microscopic description, we work in a regime where you have description in terms of, I mean, a quantum field theory living on the D branes. In particular, you can ignore gravity. So the way this matching works is that to start with, you have the black hole, its entropy, and so on, where you have a sizable Newton's constant, and then you use the supersymmetry to tune the Newton's constant, which is same as tuning the GS, to such a regime where you can safely ignore gravity, but due to supersymmetry, your index remains the same, and therefore for that particular purpose, not in general, for computing index, you can still work in that regime, ignoring gravity. And when we talk about branes in the microscopic description, we are in that regime. So I agree. This is a valid question for the supergravity side, but for the MSW CFT side, I think we are safe.
For the field theory, there's no problem. I have no difficulty there. It was the gravity side I was having difficulty with. But since we're talking about black holes, and the M theory should be associated with not with the field theory, but it should be associated with the gravity side. So the M theory circle has nothing to do with, it doesn't show up in the field theory side. So
well, it does in the sense that the M theory circle, that radius knows about the dilaton field, and the dilaton appears here.
The dilaton is showing up as the coupling of the Yang-Mills.
Sorry, where are you referring?
Oh, I'm just in general. I mean, you're. Yeah, I don't understand what's going on here. It's really the problem.
Okay, let me try to rephrase. So we don't really have a Yang-Mills theory here. What we have here is okay, maybe I'll just talk about what we have here in this MSW CFT is the M5 brane wrapping up 4 cycle, and then the fields are simply all the way these D branes can vibrate, that you can all the ways you can change the 4 cycles smoothly. Those are the fields and its fermionic partners.
Okay, so it's not a 4-dimensional field theory.
No, it's in 2-dimensional. It lives on this torus.
It's just a 2-dimensional field theory on this torus.
Yeah, because we have reduced over the 4 cycles. So M5 world volume will have 6 directions, and 4 of them we have reduced on, which leaves only 2.
Yes, but I still have a 4-dimensional field theory.
No, we have
you have 4-dimensional space-time.
Sorry?
You have you reduce from 10 to 6 or from 11 to 4, but you reduce from 10 to 4 or 11 to 4 to get your field theory and where the black holes are sitting. That's
there is 2 different reductions here. Maybe for the supergravity side, we are reducing over the 6-dimensional space, as you mentioned, and we have a 4-dimensional supergravity. For the CFT side, we start with it's good to start with, for this particular case, good to start with the M theory. So we have 11 dimensions.
Fine.
And then we have an M5 brane, which wraps a 4 cycle in the Calabi-Yau threefold.
Okay.
And
the M theory circle. Yeah.
And time also, because there would be a time direction.
Yes.
6. So what we our starting point is the world volume theory on the M5 brane. So to start with, we have a 6-dimensional theory in that sense.
Yes.
And then we reduce that theory over the 4 cycle. which it wraps,
Okay.
which leaves a theory in this torus, 2 dimensions.
Okay. Yeah, I see what you're doing. Yeah. Okay. All right. And this is a conformal field theory in the end.
At least it flows to a CFT, and that happens
CFT,
to
yeah.
capture certain things.
Okay. And you've Euclideanized this
Yeah.
theory. Okay. Oh, yeah. Okay. It's quite complicated, but go ahead.
Yeah, it is indeed.
Yeah.
Indeed.
Okay.
Yeah, so in that torus, one can check that, I mean, M theory is a way of sort of geometrizing stuff. So it's not perhaps a surprise that these taus turn out to be the same. Anyway, the lesson is that normally you would, when you have a CFT, you do modular stuff. But due to this match, you can also analyze modularity in supergravity itself. The question of the temperature in supergravity remains. I should have a better understanding, but the thing is, okay, maybe we'll come to it later. Let's move on. Yeah, now we work with some partition functions, and we'll. Are there any questions till now? I think I have confused enough.
No, I'm asking my questions as I go along, so I leave it to anyone else with questions.
Okay, so we construct this partition function. So the idea is to, so the objects of interest are these degeneracies, omega. This bar thing is a technicality, you can ignore that for now. And then this tau2 is the beta. Actually, 2 pi tau2 is the beta, I think. Anyway, so it's a, so this part, this mod z part, this is e to the minus beta h. This part, and rest are needed to satisfy certain symmetries and so on. Now, yeah, here the temperature becomes important because when we sum over these things, of course, we keep the tau2 same, but the black holes keep changing. So I would like to think of this temperature more as a formal object rather than the physical temperature, which would change as you change the black holes. Okay. Now this central charge Z, it has this form, and here we have ignored non-perturbative contributions, and in particular what is entering is the mod of Z, that is the mass, and in the large volume regime this has a particularly simple form because you can ignore this 1 over J terms. Just note that there is a J squared term, which of course is going to diverge as J goes to infinity, and the rest are order 1. In particular, this term, the last term, here, note that we have defined it to be some q hat plus a square. The hat refers to this shift by minus BP. It's not that important. The plus is important. So this J being the scalar form, it projects this charge Q to a positive direction. Remember, Q lived on a lattice where there was one positive direction and all other were negative. So this J guy projects to the positive direction. Okay, so this we call Q plus a square. It will appear later. Okay, now one important symmetry is that supergravity has is spectral flow symmetry, under which the magnetic charge doesn't change, but the electric charges and the moduli both change. This also appears in MSW CFT as the symmetry of the algebra. Yeah, this is important because since this is symmetry of the theory, the degeneracies are unchanged under this symmetry. That is important. In particular, this is called, sorry, I think I forgot to mention, this is called spectral flow. So in particular, if you explicitly compute the classical black hole entropy, it knows about, it is invariant under this spectral flow. Okay, so there are three spectral flow invariant things: this Q0 bar hat, which is the D0 brane charge shifted by this Q square guy, and then Q hat, which is the electric charge shifted by this B field and the conjugacy classes. They are the ones they'll enter. This is important because this sort of guides us how to organize the partition function. Okay. Now, for the sake of simplicity, we'll set this. There was some extra fields. We'll set some of them to 0 to simplify the expression. It's not important, just for the thing. So we had this clumsy partition function. It looks slightly better if you work in terms of this Q, which is e to the 2 pi I tau. Then it looks like this. We actually cook up a hybrid partition functions, which we call attractor partition function. It's not a physical partition function. What we do is that when it comes to the mass, that is the exponents, we use the moduli at infinity. But when it comes to the degeneracy, we use the attractor. I mean, we use the degeneracies at the attractor value, which are enormously simplified. Most of states don't exist there. Anyway, and then you can organize the partition function in this fashion. The details are not important. The only thing I want to draw your attention to is that this H guy, this is a generating function of the degeneracies. They know everything about the degeneracies. Another point is that we have sum over electric charges. And since the lattice has mixed signature, it's not immediately obvious that the sums converge indeed. To see that it indeed does, note that the exponent of Q is Q plus a square, and by construction, it has a positive quadratic form, whereas the exponent of Q bar has minus Q minus a square. Now, Q minus a square, of course, is negative, but with the minus sign, it becomes positive. So in end of the day, we do have positive numbers appearing as exponents. Are there any questions till now? Okay. I hope I'm not losing people. Okay, now we come to multicentered black hole. So what is it that we want? Let me just briefly this thing. So when you have, suppose you have a single-centered black hole, then you have this structure, and this H guy knows everything about the degeneracy. So our object of interest is this H. When you have a multicentered black hole, then the degeneracy has like a layered structure. One is that individual black holes, I mean, constituent black holes, they will have some intrinsic degeneracies. And then if you treat them as particles, forget about those degeneracies, as we did in the Kuiper quantum mechanics, then that quantum mechanics will also give rise to some degeneracy of ground states. So that will be some function which I have written F. And then there would be a product of internal degeneracies. Now, just like this H guy knew about this omega bar, here, if you can cook up, here you have a product of this omega i's. So you try to cook up, you try to massage the partition function such that you also have a product of this H. That's a natural thing to try. Now, how do you do that? So what was H? H had a sum over D0 brane charges. Okay. So here you note that the total D0 brane charge is sum over D0 brane charges of the centers. So it's sum over all these individuals D0 brane charges, which is fine. But the exponent was not quite D0 brane charge itself. There was it's Q0 bar hat. And the hat, if you remember, refers to this shift by Q square. Due to this, you end up getting some extra terms. And the important point is that they appear with troublesome signs. So you have Q bar to the power minus this thing square. And since this thing has certain positive direction, minus of this thing has certain negative direction. So at this point, we have a very simple, well, not simple, very clear problem that we have a sum in which the sum of the exponents are negative. So our immediate concern is that, do we have a convergent sum at all? Rest will come later. This is the immediate problem. Now, for example, each individual q had signature 1, b2 minus 1. There are n of them, suppose there are n centers. But since we have fixed the total charge, it's really n minus 1 dimensional stuff. So you have n minus 1 positive direction. With this minus sign, it becomes n minus 1 negative direction in your sum. So it seems that it would not converge. In fact, in general, for a general f, it would not. Only way out could be that if f happens to have some structure such that whenever this exponent is negative, this guy vanishes. If it happens to be like that, then this sum would converge. Is this point clear?
Yes, I mean that term is absent if its coefficient is 0. So yes.
Yeah. Okay. Now let's specialize to n equals to 3, and let's actually look at the structure of the degeneracies and whether we actually have that structure or not. Since we are at the large volume attractor point, we do not have two-centered black holes. We only have scaling black holes, and the simplest of them is the three-centered one. For simplicity, let's call gamma 1, 2 as A, gamma 2, 3 as B, and gamma 3, 1 as C. And they have to form a triangle, as we saw. Now, you can cook up a function which vanishes if ABC do not form a triangle. And you can check that that function is this F total. There are some step jumps and technicalities which I skipped. It's easy to see that it is like this. For example, if you take A to be much larger than B and C, of course, that would not form a triangle. And in that case, you can check in the first term, both are positive. So you have 1 plus 1, 2. In the third term, this sign, first sign is positive, second sign is negative. So you have a minus 1. And same for the last term, you have another minus 1. So it's 2 minus 2, 0. Check that. And when triangle inequality is satisfied, you can check that it's 1, except for some very special cases when it might become 1, 4. And anyway, those are marginal cases. Let's not worry about them. So what we learn is that the degeneracy must include a factor of F total. And it's not the degeneracy itself, but it's inside the formula of degeneracy. Now, we cannot solve that complete problem. So we simplify the problem that we, We imagine that the degeneracies were 1. So we just think of the generating function of this F total. Let's see what that gets. That gives us. That itself is important because you see there is this issue of convergence. So first we must ensure that the simplified version works. For that, let's just note that we can express ABC as product of this some vector C and Q, where C is a 3-component vector made of these magnetic charges, and Q is this Q1, Q2, Q3. So in the partition function, we'll have sum over these Qs. Now we come to known facts for this convergence, which come from mathematics. Anyway, the detail are not important. The point here is that if you have a sum of this sort, which we do, then, and if you have a kernel, this curly K, which has, this is basically 1, the first term, 1 plus sum of product of signs. We have exactly that structure. We have a 1, and we have 3 terms which are product of signs. Then there is a certain condition, and it's sign of inner product of the vector x, which is being summed over, that is the electric charge vector for us, and some vector v. And then we have certain conditions called Funke-Kudla conditions on those vectors. which if they're satisfied, then this sum converges. There exists such a statement. Since we have exactly that structure, we check that for our vectors, and we find that indeed they are satisfied. Questions?
Just that's some of signs that you've written there. It reminds me of the ARF invariant. Is it by any chance an ARF invariant?
Sorry, what is that? I don't know. Sir.
Okay.
Okay, yeah, maybe we can talk about that later. Yeah.
You think things mod 2, don't you? And
Sorry, Charles?
I think you'd need some more things mod 2 for it to be off invariant.
Well, signs are mod 2.
Yeah, but they're multiplied together.
But that's what happens in the ARF invariant.
So I think I have to plug my laptop. My charge is sorry. Dying. Sorry. Any questions? Sir? Shall I proceed?
Yeah, please. Yeah, please. Yeah, please.
Yeah. So, so we see that the sum converges indeed. Okay. Now comes the modular completion. So, although it converges, it doesn't have the necessary modular properties, and there exists this standard machinery of modular completion, where you add a certain term such that the whole thing has nice modular properties. The thumb rule is that when you have product of signs, you replace this by double error functions. There are some technicalities in that, but yeah, that's the thing you do. So in particular, another representation of error function is sort of important, where you have the original signs that you start with, and these 3 extra terms you add. And they have nasty expressions in terms of various iterated integrals. Okay. Okay, so that's what I do. So just to remind, we started with this HP mu, basically contribute, which tried to contribute the tried to compute the contribution of 3-centered scaling solutions to these objects. And then that problem was tough, so we considered a simplified problem where we imagined that the degeneracies were 1. So we just looked at the conditions of their existence, and that contribution, that partition function, it we showed that it indeed converges and computed the modular completion. In our paper, we also did some progress for the contribution from the regular part. I didn't talk about that. And the point is that end of the day, we can still preserve modularity, although the cost is holomorphicity, because this tau bar appears in this extra E2. There are some okay, and one immediate future problem would be to work out the exact problem, which is to reinstate the degeneracies, which are called pure Higgs degeneracies, and see how things work. Perhaps less ambitious thing to try would be to see that whether like the scheme of things work for quivers with like more nodes and more loops. I guess that's all I have to say. Thank you.
Okay, thank you very much. Stuff Walter Rose. Very nice. And if there are any questions, at least I've asked lots of questions as we went along, so I'll try and be quiet.
I appreciate that Kitos in the middle. That's finished.
Yeah.
Okay.
That was a very good talk. Thank you. Yeah, I was a little bit distracted, and this is not my field of research, so it's quite new to me. But when you join DIAS, I'm sure you and I will have lots of discussions. But it was a very good talk. I really enjoyed it. Thank you.
Thank you.
Sure, then if there are no other questions, we can at least stop the recording and go to less formal questions. Okay, so I'm going to stop the recording. And thanks again, Swapnamay.
Thank you.
I have a question for Denjo. How do you read the Irish version?
Gorev Mahogot. Gorev Mahogot. It means that good may be to you, may come to you, or something roughly like that. Gorev, it's a wish. It's a wish for good to come to someone, and it's a standard thanks. Saying thanks, you say good, maybe good wishes to you. Literal translations, as you know, never work.
Yeah.
It's a bit long.
It's a bit long. Yeah.
Is there a shorter version of thank you?
Is there say it quickly?
I'll say it. Oh, that's challenging.
Yeah. I can't think offhand of a shorter version.
I see. Okay. You haven't stopped the recording, by the way.
I did. Sorry.
No, it's distracting you.
Yeah, I should answer